Jorge Ortiz. He's assistant professor in our Rutgers University, and his interests are in building and studying sensing systems like smart objects, smart built environments, and more broadly, smart cities, systems that engage with humans, either learn about them or operating feedback with humans or cooperate with humans in enhancing our lives. Jorge has, in addition to his academic experience, also a pretty remarkable industry experience. First, as a staff member at IBM Research, even before even an Oracle. He has, he's inventor of about 12 patents and published and won also either Best Paper Awards or Best Runner-Up Awards. And he has also been leading projects where actually research got commercialized and brought to market. So before that was even an Oracle. He has been working in co-founding or funding or leading multiple startups too. So he's a Berkeley PhD student, and he will tell us about the research on intelligent system, human-centered intelligent systems. So I'm looking forward to hear from him. Join me and welcome Jorge.
Thank you very much for that introduction. It's a pleasure to be here, even if it's just virtual. It's really nice to just have that kind of interaction and to have a space where we can share our ideas and our results, even though we can't be co-located. So I hope everyone's doing well and everyone's very healthy. So as was mentioned in the introduction, I study sensing systems, and I've been working in sensing systems for a long time, for about 15 years now. And lately, I've been focusing on how humans can play a role in making intelligent systems smarter and more adaptive. So I'm going to give you a little bit of an overview of some of the work that's been taking place lately in my lab, where we try to understand sensing systems in the context of human use. So we know that IoT as a whole continues to grow at a tremendous rate. We're seeing more and more IoT devices embedded in our lives, in our spaces, making our homes smarter, being able to control things remotely, whether or not you're home, having those sensing systems interact with you directly in order to understand your preferences, for you to order your next new item from Amazon, or do a search on Google that may appear on your home screen. We're seeing devices implanted on ourselves, not just for health and fitness, but also for chronic disease management. So in many ways, we're are taking all of this sensor data, already learning about our behavior and our buying preferences, but also about our health condition. Within the systems that we live in, we're also seeing the connectedness of these sensing devices. So in smart buildings, for instance, understanding the operational use of the building, not just maintaining its energy consumption low, but also what kinds of activities are taking place within it. And every day, because of the market forces, we see new and new IoT devices hit the market. And so it becomes an interesting question. What do we do with all this data? And more of this data is interacting with its users. How do we make truly intelligent, robust systems with the help of human interaction? Overall, even at the scale of a city, we need to answer these more fundamental questions at a smaller scale in order to build up this system of systems at city scale. So for instance, there's a separate project where we're looking at, that I won't discuss today, where we're looking at human activity within the city around COVID and how that has affected rates of transmission. So there's ideas about using sensing systems to learn human behavior, but also having humans feed back and interact with those systems in order to make them smarter. If you look at the IoT market size, we see that it's a multi-trillion-dollar market. It's projected to grow to over $11 trillion in 2025. And the segment of investment in human-facing IoT systems is about half of that. So The market, the space for health applications, initially for fitness, which is a big market, but disease management and aging at home is a big market. Smart buildings continues to grow. It used to just be about energy management, but now is becoming more about productivity. So clearly a human is part of that equation. And vehicles. Interestingly, when people think about IoT and vehicles, they think self-driving cars. And yes, self-driving cars is a big part of the story. But it's actually the effects of self-driving cars, rethinking how vehicles will be used. No longer will we be driving them, but they will be shuttling us around. And thinking about those as interactive spaces starts to come to the fore as far as a research question. So more broadly, thinking about sensing systems and human cohabitation, we have these huge buildings with a number of sensors in them, vehicles with sensors in them, more and more AI to extract meaningful information. And from a lab's perspective, this is very interesting because it represents a wider body of computational and information challenges of complex sensing systems and their interaction with humans. So for this talk, I'm going to focus on 3 fundamental questions. The first question is, how can we build robust intelligence into sensing systems? We often find ourselves dealing with supposed intelligence that breaks quite easily. We see this both in the design of machine learning techniques, but more so in the design of even the dumbest of sensing systems, that do occupancy detection, for instance. The second question is, how can we use sensing to incrementally understand and make sense of context in smart spaces with the help of humans? So what we'd really like to do is to use ambient sensing to understand what's happening in the space and how it is that those activities are modulating the signals across multiple physical channels. It turns out that question is quite hard, and we assert that actually a human in the loop is necessary in order to learn this raw data to concept mapping. And the third question in a separate project that we're exploring is the use of multimodal sensing to basically understand both context and human reaction to that context in order to determine when is the best time to interact. When should an intelligent agent interrupt a human to ask them for a label, to give them information? How do we basically take all the sensing, this rich sensing fabric, to essentially make sense of it for a particular goal, in this case, when to interrupt. So in the first question, we're going to explore this question in the context of a project we call Patient Sense. The second one will be, we'll explore it in the context of Project Maestro. And the third one is in Project Pause. And feel free to ask me questions via the chat if you have questions along the way. So in Patient Sense, we designed a smart pill bottle. And so this is this notion of having a smart object. If we embed sensing into this smart objects in the context of this smart pill bottle, what can we learn about our users? So the particular application domain where this is important is basically around healthy aging. Between 2006 and 2030, the US population of adults over 65 will nearly double from about 37 million in 2006 to 71.5 million in 2030. And of those who are age 65 and over, almost 90% of them want to stay at home and in their community. And in order to do that, we're really going to have to essentially move aspects of clinical assessment to the home. That means we're going to have to monitor mom and dad as they age, figure out, whether they're engaged in healthy habits, whether there's an aspect of these observations that may indicate deterioration, whether they're taking their medication. These kinds of questions come to the fore. Medication adherence in particular is a huge problem in the United States. And there's a lot of existing work in relation to sensing in this area. There's proximity-based sensing to make sure to determine when you're close to your pill bottle. There's vision-based systems that classify who is near the pill bottle or the medicine cabinet and when they've actually extracted a pill from the from the medicine cabinet. There are ingestible biosensors, wearable sensors, which are pretty uncomfortable. Here's an example of one. There's actually a board that goes on your neck and tries to detect when you've swallowed. And there's smart pill bottles, and there's some quite a bit of work in the smart pill bottle space, mostly around essentially binary sensing. Someone has picked it up, someone has opened the pill bottle, and given that, we believe that the pill was extracted. So we thought smart pill bottles would be a good solution here. They're unobtrusive, we can make them very low powered, we can equip them with extra sensors and extract all sorts of user behavior. So the first goal that we started with is to determine whether we can determine whether we can classify who is interacting with this pill bottle. So we ran several experiments with users and realized that as they were extracting these pill bottles, the way that they extracted it was unique to that person, or at least that was the initial hypothesis. Some people take the bottle and sort of twist it over to remove the pill. Other folks, some people are right hand dominant, left hand dominant. Other folks sort of hold it close to them and insert their hand inside. And so we wanted to see if this subjective observation would be realized in the data that we're collecting from the bottle itself. We inserted 2 accelerometers, one in the cap and one inside this 3D printed bottle. And these sensors are essentially activated when the pill box is opened. They run on essentially on a coin cell battery, and they report their readings over a pip tag, which is just a wireless transmitter that's sitting on the device, and it's a low power device that sits on the bottle. The overall pipeline is essentially, we brought some users in in a naturalistic way. We just asked them to extract the pill from the pill bottle. And we collected the data from these users. Then we essentially did some pre-processing on the data that we collected, building up a dictionary and passing it into a classifier in order to identify who the patient was. Just a quick view of the power consumption analysis here. We can see that it was actually the platform was optimized to consume very little power, and so this makes it a realistic solution for real patients. So going back to the algorithms, specifically, we did a bag of words construction. So this is an example of the trace that we got from the accelerometers. We got these X, Y, and Z traces. We extracted these pulses. So anytime we saw any reaction or some response in any of the measurement channels for our accelerometers, we would slice out the segments that were near zero, where there was no modulation. And we created a bag of pulses, a bag of these modulation patterns. So we put them all together into a single bag. And we ran a distance algorithm essentially to just build up a pairwise distance matrix. From this matrix, of course, you can run a standard clustering technique. And from this clustering technique, this essentially gives us a dictionary. So now we have a label for a particular modulation pattern. So for instance, here's an example of the modulation pattern 3, right? Because it fell into this blue cluster. We see that when I extract the pill, for instance, I generate a 3 and a 5 and a 3, or in the x-axis. I may also generate a 4 and a 3 in the y-axis and a 5 and a 3 pattern in the z-axis. And so if you look at the bottle data and the cap data next to each other, after we've extracted the individual pulses, we take the dictionary and we map each of these pulses into a dictionary, generating a sequence of these patterns, right? So instead of having the raw data, we now have a sequence of patterns that falls into one of the k different clusters for our dictionary terms. And we concatenate these two as our feature vector, which serves as a pseudo signature for the end user. In our evaluation, we recruited 16 healthy adults, 14 males and 2 females. We use a camera for ground truth. So this is just to essentially map the trace to an individual user. And with a fairly simple shallow model of multi-class SVM, we're able to get over 90% accuracy with 3 subjects, being able to accurately identify who the user is. And with over 16 different subjects using the same model, we still get over 85% accuracy. So, you know, the model is still pretty effective. This general featurization technique is effective. We think that it goes beyond just being able to identify the end user. While identifying the end user for medication adherence specifically is somewhat useful because we can track who's taking it, there are lots of conditions where tracking the end user isn't necessarily helpful, because if for older patients, other people may be extracting the pill for them, but we could at least identify who it was that was extracting that pill. There are other use cases, medical use cases, where being able to classify who the user is useful. For instance, nurses will hand out pills to patients on a floor, and they go to a general sort of stock closet with different types of pills. And you could check if the authorized nurse extracted the right pill, right? The problem with this particular technique, however, is that we're only able to, with 3 subjects, we can identify about 90%. With 16 subjects, you can see that the accuracy drops and the recall doesn't do so well. You can see that it's sort of monotonically decreasing for the most part. So we wanted to see, okay, well, can we build a model that has higher capacity for differentiation between different users? And can we build one where the number of samples we need per person is maybe less? The reason for the second part of that question is that we're also designing new pill bottles for which we wanted to apply the same algorithm. And so this is a classic formulation. This is a classic example of where you'd want to do domain adaptation. There were model capacity limitations. As I mentioned, we were using shallow models in the first iteration. And by model capacity, I mean the ability to differentiate different types of users. The data set is very small, so we had to come up with ways of either attaining lots more data, which would require perhaps a clinical study, or just a much larger, longer study, which we are in the process of actually performing now. Or being able to embed a model that we can essentially make use of prior knowledge in order to quickly bootstrap its performance. Proper differentiation is necessary so we can reliably, especially in the second context, we want to be able to differentiate more than 16 users with high accuracy. So in the first approach, we first tried domain adaptation. We generated these 2 generations of 3D printed smart bottles. And we did something we call domain casting or input casting. And that's taking time series data and casting it into the visual domain, and then using transfer learning models for visual domain models to identify users. And I'll give you an example of what the new pipeline looks like. So in this new pipeline, we collected more data from the same set of users on the second generation of the bottle. They generate their raw IMU measurements for performing the same pill extraction activity. From these, we cast these time series into the visual domain using recurrence plots. So we generate these recurrence plot constructions, which are basically a function that maps a time series to a matrix with some color and different patterns in it. And we'll show you an example of what that looks like for different users. And we feed these visual representations of the input to a pre-trained CNN. We remove, again, classic transfer learning. We remove the last couple of layers that do classification. add our layers of classification, our dense layers for performing classification, and then retrain the model using the visual features extracted from the recurrence plots. And then we go ahead and test how good our performance is. So here's an example of a recurrence plot. The details of recurrence plot generation, there are many, there's a few papers that actually do this, and we describe it in our paper as well, which is we currently have under submission. You can see that when we cast, so with the time series visually, it was hard to see that there was a sequence, and we do have these handcrafted features that we were, that we devised ourselves, essentially with the, thresholding the extraction of pulses and using clustering to learn the dictionary. But here we're simply applying the recurrence plot construction algorithm on these, and you can clearly see that visually, and the color matters here as well, that the users are very easily differentiable, right? So you can immediately see that user 1 and user 2 look very different, both in color and texture of the recurrence plot that's generated. Here's the source bottle recurrence plot of the same activity for a single user. And here's the target bottle. In some cases, the transfer isn't perfect as we go from source to target. You can see that actually the pattern looks quite different, especially for the target bottle on this second instance. The reason for this is because the sensor was, the first generation had a cap that you can simply remove. The second generation has a twist off. And so it just generates a totally different modulation scheme, modulation pattern than the first one. However, we are able to outperform the initial model, even with classic domain adaptation techniques. Here we wanted to test sort of the fraction of labels that were necessary, and we still needed quite a few. Essentially, we weren't gaining much in terms of domain adaptation, but we were gaining a lot in terms of model capacity. So in other words, we're able to differentiate many more users. The other trade-off here is that the model is much more complex because it's higher capacity. And there's a question of how you would miniaturize the model to run it on the pill bottle itself. If you don't run it on the pill bottle, so the trade-off is if you run it on the pill bottle itself, the battery runs out faster. So you have to think about the implications of that. The other option is to run it at a server, but there are complexities with transmitting the data. I think that transmitting the data is okay, simply because for this particular application, we care about the historical use of the bottle, who was using it, when were they using it. In a situation where you needed to do something more interactive, more real time, but clearly the high capacity model would not be your primary choice. Okay, so basically here, the main objective, again, just to remind you, is can we build more robust algorithms? And it's clear that with higher capacity models that have less bias, that you can train these deep learning models based on the data, actually do a lot better. So going back to our second question, we look at Project Maestro. And so Project Maestro is an ongoing project now. We have a platform which is shown here in the picture. I actually have here on my desk as well, which is performing ambient sensing. And the idea is it's quite hard to acquire labels in situ. So is there a way that we can automatically build a system that discovers labels over time through interaction with an end user? So the motivation, again, going back, there are many complex different types of interactions that happen in a space. Current machine learning techniques don't generalize well across sensing environments. You'll typically see a lot of work in the literature where they tried it in one room, perhaps two rooms, where they're doing activity recognition. It's clear that if the placement of these algorithms tend to be sensitive to the placement of the sensor, the location, the sort of physical layout of the room. Human activities generate these unique spatial temporal patterns across multiple physical phenomena measures, right? So essentially, whenever you perform something, it's not, or you're engaged in some activity, it could be that you're generating a vibration signal, sound signals, visual signals. If you're using any sort of electrical equipment, you're going to see a spike in the use of the magnetometer measurements, in your shadowing. So there's a lot of different multimodal sensing modalities that we can use to try to essentially make sense of the world and build a sort of semantic map. And it's clear that and it's, it's not unique to this space, but there's certainly this semantic gap between raw data measurements and the labels that are needed to make sense of them. Clearly, the labels are required in order to learn them. And in many instances, because of all the variability and the way in which the signal to noise ratio can change pretty drastically depending on placement factors and the location of the physical layout of the space, human feedback is necessary. So there's already some related work in the last few years on this. There's this notion of synthetic sensing where you can build multiple sensing layers from the zeroth tier sensing layer, which grabs only raw data across multiple modalities, to in a layered fashion, essentially use the pre-trained labels to build up a state machine to determine what state various devices in the environment are in. The drawback with this is that anytime you want to introduce a new label, you have to explicitly run the experiment to teach the system what this label is. So there is I'm going to, you have to tell the system, I'm going to turn the dishwasher on, or I'm going to open the dishwasher now, and you have to start it and then go do it. And then you have to wait for the model to train on that new signal. The other drawback to this approach is, of course, that it's brittle. Right? So the way that the dishwasher sounds and vibrates may be different in this kitchen versus that kitchen. And so there is no intelligence there with regards to those types of changes. Again, you can take the raw sensor readings and individually partition them into what's happening. These particular semantic maps, or these mappings from multivariate time series segments to label, were all done in a controlled experiment. The question is, how well would this generalize? Why can't I have an algorithm that picks these out and then presents them to me proactively? So rather than me having to train the system explicitly, what we're aiming for in Project Maestro is for the system itself to say, I find something that's statistically interesting. What do you think this is? Or, hey, I find this statistically interesting pattern that looks a lot like the microwave being on. Is that also the microwave being on? And that will give us a better idea of the variance in the signal for a particular activity. So recently, there's also been some work at Facebook called Semantic Maps, where they have an active robot record audio-visual signals of different spaces and remember where objects are placed, what those environments sounded like, what kinds of events are happening in those spaces. In order to generate this data, the audio-visual signal, basically a video recording on a robot, had to be manually labeled. And so, of course, this is related. We'd also like to be able to place these anywhere and to generate a map of what we think is happening in the surrounding space, to measure the agreement across different devices and across different spaces, and to build up a map of ambient sensing signals across space and across time. So I see this work as complementary to what we're trying to do. And so the fundamental question here is, how can we learn these semantic concept maps via passive ambient sensing and active labeling over multimodal streaming data in situ? So that's the other aspect of this, which I think is really important, that gets overlooked, is that the label should ideally happen while the event is happening. It often is the case that the camera will not capture the full context. And so it's best to have a system that at least tries to proactively ask you while something is happening so that labels aren't missed. And so that's also an important aspect of our objectives here. So as I mentioned, we've built up a platform called Maestro. It is a sensing platform with 9 or so different sensors, I think 9 or 10 different sensors on the platform, generating 18 different sensing streams. There's also a camera attached to a Raspberry Pi, and so these two are attached to each other. The reason that we use the camera is for times when someone isn't actively labeling, so that we could record some notion of context and at least acquire a label for interesting events. So while we prefer for the user to actively engage with the system, i.e. the device is listening, and when it finds something interesting, it asks what this is, it's often the case that, you know, the user can't be there all the time. So we do need to record some sense of a contextual signal. And that's what you see here in this UI for Maestro, where there is a video feed, there's a sensor, there's some detection of an activity, and the video shows what synchronous video was collected in conjunction with the multivariate signal. So we've applied we've tried to build some applications on some of the labels learned through Maestro. One was for simple occupancy counting, use identification, like what the things are being used in the environment, what are the different spaces being used for, excuse me, and activity recognition. And we're building up a suite of different applications based on this interaction between Maestro and end user labeling. We've applied active learning techniques just simply to show that there is consistency across the signals that are being measured. You don't need very many labels. So each line here basically represents how many initial labels for an activity that were available. And this shows how the accuracy grows with more questions being asked by Maestro. And so this is just a pure application of active learning using uncertainty sampling for simply identifying these are interesting. This is an interesting segment in your data. What was happening when we collected this? Why did it change? So the two areas of active work in this space, if you notice in this previous graph, we had to have some initial set of labels. Those initial set of labels happened through active experiments in a controlled setting. And that's one of the things we want to avoid. We want to actually bootstrap the whole start of the system, where you deploy, the system immediately starts to listen, finds interesting events, asks you what they are. We are developing models to do context representation. So is there basically contextual embedding that would be robust to changes in the environment, robust to different placements of the sensor across different spaces in order to discover unlabeled events? The second one that is more subtle is change point detection. It actually plays a fairly big role as you're streaming data in, because it's not clear what constitutes a sample. So whenever I feed my algorithm, whenever I feed my data to a model, I need to decide a priori how many samples constitute a sample, how many individual readings constitute a sample. And it turns out that this is a really important question to answer before you even trust your classifier at the end. And I'll talk a little bit more about the development there. So in the development of a new featurization technique, we're looking at a technique that we applied previously for identifying IoT devices in the wild. This technique was based on spectroscopy, where essentially you take, and I'll explain the notion of spectroscopy and how we applied it here, where light comes in from the external world, it passes through a spectrograph, which essentially disperses the light in interesting ways. And this dispersion factor tells us the physical makeup of what's in the light. So we want essentially an information version of this that is able to scatter the data into an interesting distribution so that we can make sense of the what's happening in the world. Okay, so in this previous work, what we did is we took essentially a stacked autoencoder. We had a unsupervised learning representation that gave us features that we can cluster into a scattered pattern. So it gave us a diverse set of features for different types of traffic patterns. And so what characterizes a device are the types of traffic patterns that it generates. So for instance, here are essentially we learned the features in an unsupervised fashion. In this particular context, we took traffic data, pass it through a stacked autoencoder, training each layer at a time in the standard stacked autoencoder technique. Then we cluster the features after the autoencoder converges, after the representation converges. That is that you pass in an input and it does a fairly good job within some bounds of reproducing the input. When we run clustering on it, we get nice behaved clusters. So essentially it's like learning a dictionary. And now we can go back to looking at the data that's generated from the device and see what dictionary terms it outputs. And so the dictionary terms are one of k different clusters, and the distribution over those k clusters represents the activity of the device. It represents the device. So for instance, here we're looking at the histogram generated for the distribution over 100 different clusters. So you see that the Android phone has very many different types of traffic patterns. It has a distribution that is pretty complex because there are many applications running on it. Whereas a Belkin motion sensor doesn't have that many because it's a pretty dumb IoT device. Whereas the instant camera is somewhere in between the Android phone and the Belkin sensor. Okay, so this is simply a motion sensor. It's probably sending traffic back home to the server saying, here I am, here I am, here I am. Occasionally, it may respond to external stimulus, like someone coming in a room. The instant camera is sending different types of pictures. So of course, you also expect that the type of bit patterns that you see in the payload will be more diverse. But an Android phone basically looks like a mini computer. Now, since we train a model such that we get distributions where we can differentiate different types of devices, we can essentially cast that into a probabilistic framework and then use probabilistic measures to measure whether the pattern that's produced by an individual device looks like the pattern produced by another one, right? Whether two distributions are similar. So we're looking at this multivariate context in Maestro and saying, do different labels across different spaces look like this? And I think a probabilistic framework is the way to accurately characterize it because of the changes in signal to noise ratio, but where there's some underlying structure, we believe, for specific types of events. So the second one, as I mentioned, is much more subtle. It's this notion of change point detection, which I think is often overlooked in the sensing space. The idea is we have sensor data that's streaming in, and it's not clear how you decide how many measurements make up a sample. And that's a fundamental question for doing any sort of modeling downstream from segmentizing your data. Now, we noticed that for a given data set, if we pick arbitrary segment sizes, we actually get a big difference in the performance of our classifier downstream. So we ran some experiments on some of the data we collected. We picked the smallest segment size for given the ground truth. So the ground truth actually segments the data into different events. When we use the smallest segment size, we see the performance that looks like this set of bar charts here. When we use the largest of those events to constitute a sample, we get much lower performance because we're sort of conflating multiple events together. Here, we're not capturing events that are over longer periods of time. And when we run the exact given the ground truth, a human actually segmenting it, we actually get the optimal performance. And actually, it's much more nefarious than this. there's a paper dating back, I think, to 2012, where they show that that choosing arbitrary segment sizes leads to arbitrary results. So it's even a much stronger assertion than this, which again necessitates the need for doing something more systematic like statistical change point detection. So in our change point detection scheme, for folks who are not familiar, it's essentially looking at, in the time series context, looking at a set of measurements before a change point and after, or considering a point in time that segments your data into two segments, and then looking at the collection of segments before that point in time and the collection of measurements after, and deciding whether they were drawn from the same distribution. In our solution, we used maximum mean discrepancy as a measure of similarity. This essentially looks at the interdistribution distance according to a pre-selected kernel. So these are the two distribution distances, and this is the cross distribution distance. So if X is drawn from the same distribution as Y, then the value of this is very close to 0, because essentially these two add up to 2 roughly, and this is 2 times the same value. Or sorry, each of these is 1, so they add up to 2, and this is about 1 as well. So there's a bunch of theoretical work. There's a number of papers in the theory around MMD where they test different kernels and different ways of learning the optimal kernel to get maximum separation between different distributions. And we went with a Gaussian kernel. And we actually tried multiple variations of this, but we used a Gaussian kernel in our problem formulation. So our deep learning based approach for doing unsupervised change point detection basically has 2 autoencoders looking at the left side of a potential change point, the right side of a potential change point, and this MMD function with using the Gaussian kernel. And what we ended up finding actually, so once this actually converges, we can use the MMD value of 2 encodings, of these 2 embeddings, to determine when the MMD value spikes high, that those are the most likely locations for the change point. So the reason we think this works is because what you have here is you have a network that's being pushed to reconstruct the input while keeping the distance as small as possible. Okay, so in most cases, when you look at your data and you're sliding through the data, most XL, XR pairs are going to be from the same distribution because change points are relatively rare. And so that's going to basically learn a set of weights that is able to reconstruct your input. In cases where XL, where the 2 subsegments come from different distributions, your model is already biased to minimize reconstruction loss, and it becomes difficult for MMD not to take a hit in those cases. And so MMD tends to spike. You can make slight adjustments in your reconstruction and your reconstruction weights, but you know the learning rate actually causes those weights to only be updated a little bit. And so the term in your objective function which takes the biggest hit is your MMD, and that's why it tends to spike. So in practice, we actually tried this on, we tried it on 4 data sets that are common in the literature, which have a number of different change points in them and change in, you know, by an order of magnitude in the number of instances or in the number of measurements. We compared against other change point detection algorithms, and we outperform the state of the art is KLCPD. It uses a generative model to generate new samples to learn the change point. And so we actually outperform KLCPD in 3 out of the 4 data sets. And in the case where we lose, we don't lose by very much. So that's a nice result. The thing that's the biggest win and why it's a fundamental component of Maestro is that training is trivial. It only takes a few seconds to train, no more than a minute and a half across these 4 data sets. Whereas KLCPD couldn't finish for the last 2 and took hours to train on the first 2. So we have written a library. This work is under submission as well. But the basic premise here is that in order to truly find what the underlying samples should be that we should be labeling and performing active learning on, change point detection is one of the fundamental elements of the pipeline for slicing your data as it streams in. So we actually, we also tried, so the name of the algorithm is called Cadence. We tried Cadence on the data collected from Maestro. The cool thing is, so here's the output of the various, a few of the sensors that Maestro collects. The red lines represent where the user labeled a change in activity. This is the change point score outputted by our model. You can see that at times it spikes and it's a little bit off from the exact location of where the human believes a change point took place. We see that there are these spikes here which are not captured by a human, so there may be things here that don't, there may be aspects that don't show up that the human may not perceive, but that we believe is a change in underlying distribution. The interesting thing that we did see was this spike that occurred in both segments of the data. And those actually corresponded. So we alerted the user about these 2 spikes. And it turns out that that was the user vacuuming. The spike was caused by a change in the magnetometer. And the user did not record that, but our algorithm picked it up. So we saw this spike, we set the threshold at a particular level, and it said, something interesting is happening in your data. We don't know what it is because you haven't labeled it, but it looks like a change point has occurred. In fact, it's this here. And that turned out to be vacuuming. So the cool thing about this is that for being able to attain labels continuously, there are just things that a human labeling process, it's just very noisy. And so having these statistical tools with this active feedback allows us to not miss certain events. I just want to mention, I just noticed that there's some Q&A questions. I'll get to them at the end of the talk. I literally just noticed them now, so I realized that they were from earlier slides. So the final project I'll talk about is Project Pause. And the fundamental question here is, when is a good time to interact with the user? So we started with a data set that was collected in an active vehicular setting. In this data set, we collected automotive data, physiological data, and visual features. The automotive data comes from the CAN bus. So this is, includes things like vehicle speed, the brake pedal angle, the accelerator pedal angle, the steering angle, the direction of the car. We took physiological measurements. So we had a number of sensors placed on the driver's body as they were driving a fixed route. And we have visual features. So we have cameras inside the car. There's 3 cameras inside the car, one from behind the driver, one in front of the driver, one on the side of the driver. And there's an external camera, which is facing the road. And so the physiological and visual features for 3 out of the 4 cameras are capturing the physical state of the person, their expression, their body language, where their gaze may be. Physiological is just their physiological response, and the automotive data is looking at how they're interacting with the car and what the context is outside. So here's just a short video example. Oh, I forgot to mention, we have an agent that randomly asks the user, is now a good time to interrupt? So here's just a short video of what that looks like. And so with each of these, as we continuously measure all of these different variables, we also record the response of the end user. So the end user will say, yes, now is a good time to interrupt, or no, now is not a good time. Whoops. So our objective was to build a model that, using this data, is able to infer when is a good time. Again, we have the external camera and the sort of system or contextual factors. These are looking at the state of the car or the form of interaction with the car, the external view of the car, and the internal camera and the biosensors, which are these human factors. And is there a way of merging these in order to guess when is a good time? So in our model, we have all of these different sensor streams. We take, for the physiological data and the CAN data, we extract various time series features. For the front camera, we use mask RCNN, so we're not using the raw video, we're actually just using object counts as our feature vector. And for the driver, we run OpenPose, which gives us body position, face gaze, hand positioning, and the state of the hands as well. So all of this information, so the output of OpenPose is what's used as input to the model. The object counts in mask RCNN is also used as visual input to the model, and these two are combined with these measurements in order to build this model. We formulated this into a multi-branch deep convolutional neural network. So on one of the branches, we're incorporating the OpenPose information using a multi-layer CNN. On the other two, we are concatenating the mask RCNN features of object count. So we have a long vector for, where each entry in the vector represents an object, and the value of that element in the vector is the count of that type of object. And we use an importance ranking scheme for tracking the most important time series features, and that's concatenated as well to the features that are extracted from this portion of the branch. So these three branches are come together and get concatenated to capture full context and perform classification. So in our results, we see that the addition of different types of models perform better. Of course, our model actually outperforms all the other ones. The standard DNN with PCA, we tried different featurization techniques. Ours does the best. We get about 68% accuracy, which is not great, but it is better than basically all the other models that we tried. So it's still a pretty hard problem to determine when is a good time to interrupt. The interesting thing, however, is that although we get about 68% accuracy in inferring when is a good time, we can adjust the loss function in order to minimize the number of false positives. So what's a false positive? A false positive is this really untimely interruption where the agent interrupts when it is not a good time. We want to avoid those completely. And so we just basically penalize the model for getting false positives, And we're able to bring the number of false positives to 1 with by weighing false positives 10 times more than false negative than true positives or true negatives. Although the model ends up being much more conservative, so it doesn't ask as much, we find that over the period of a 1-hour drive, we still have 20 to 30 minutes of interruption time, dispersed throughout the drive. So plenty of time to interrupt and have a long, a long interaction where it's safe. This is also ongoing work. We're now looking at the perception of the driver with respect to safety. So we're now basically looking at different formulations of this model, looking at different features that may be richer. So you can see that in our model here, we're actually just taking the output of mask RCNN and open pose, but we're looking at taking the actual feature representation inside those networks and feeding it into the model instead, because we think that'll be a richer representation of the general context. The second aspect of this that we've been working on is getting a third party to look at the video and assess the safety. And so we want to not just train the model to infer when the driver will think it's a good time, but to infer when the driver thinks it's a good time and an external observer thinks it's safe to ask. So that's, again, ongoing work right now in the lab. So in conclusion, we started off with 3 questions. The first is, how can we build robust intelligence into sensing systems? We found that domain casting does improve robustness. We're able to increase the capacity of being able to differentiate various users. The performance degradation is much shallower from one bottle to another using this domain casting technique of casting into the visual domain. The second question, how can we use sensing to incrementally understand and make sense of context in smart spaces? We saw that change point detection and active learning are important elements of this pipeline. And again, this is ongoing work. So we're hopefully after COVID able to do a broader test bed development where we incorporate active learning and segmentation to learn labels and compare how concepts look across different spaces. And the third question is, how can we build multimodal sensing to decide when it's more natural to interact with a human? We saw that timing is everything. If we just get the timing right, we'll determine when is a good time. And in fact, the hypothesis we'd really like to test is whether timing is good from an agent perspective. If I ask you at the right time, do I get better information from you that allows my knowledge about the world to converge faster? So again, there's also some initial work in that area where we've seen some positive results, but we're exploring that further. Very quickly, I want to just thank my collaborators and my students across various places, undergraduates, graduate students, and various institutions. They continue to be great partners in this exploration. And that's it. I want to thank everyone. I want to thank Pierluigi for the invite, and Bhaskar as well. And I'm happy to answer some of these questions.
All right, thank you very much. And we are set here to solve very important problems also in the domain of safety, like anomaly detection for cars as well, and interacting with the user. Yeah, let's open the space for questions. And there are actually a couple, as you mentioned, on the question and answer Q&A. And everybody feel free to post on both the chat or the Q&A, or raise your hand if you want to just expose your questions directly. Okay, so the first one that we got was, I think, related to the patient senses and to the domain casting issues and so on. It's more practical, I think. Okay, so one of the students suggests, okay, what shouldn't we use fingerprints and so on, right? Identify a person, and what is...
So what do you mean? Oh, you mean fingerprints on the actual device. Yeah. So that's a good question. You can certainly explore that. I think for our generation, that would probably work quite well. I find that, older folks just have a harder time interacting with that kind of technology. Again, works well in principle. In practice, there's certainly a cultural and age-related component that makes that a less natural form of interaction. But again, it's also pretty cheap to do, so I think that would work quite well. Right.
I think probably the intuition indeed was, so if I may just ask on top of this, so the idea of resorting to vision essentially and transforming them from time series data was mostly motivated by the fact that, in fact, actually, I think time series are very hard to learn somehow, and then mapping to a vision, and there instead we have a performance guarantees of many of the tools that are already provided. Yeah.
I agree.
And
I agree.
so concerning the second system, I believe was the Maestro. Hussein asks to differentiate the users and thus increase the capacity. Use a serial number also associated with each chip instead of depending on reading difference between the pulses. Well, yeah, it's a.
You mean a serial number to person mapping?
With
yeah.
chip.
Yeah, so you would have to register the device, right? I think that's what.
Right.
I mean, here the learning bit is sort of implicit. So even if I were, and again, for folks with chronic diseases, they're typically managing multiple pill taking regimens. So they may have multiple smart pill boxes, or maybe they have one pill box or a set of pill boxes. The aspect that we're looking at with respect to robustness now is not just related to robustness to model capacity in terms of being able to differentiate more users, but also just wear and tear. So, people may have conditions where they drop it or they just have the sensor for a long time. The battery may be running low, which may be changing the capacity of the system to collect measurements accurately. So noise is, introduced. And we want to build robust features in the context of all this noise as well. So I think the deep learning models are pretty robust to noise if you provide enough samples. And of course, that's the challenge, providing enough samples, which is why transfer learning we thought would be a good approach.
One quick question actually on the Maestro I was also having in terms of it was interesting your approach in finding the anomaly or the difference in the distribution using kernels. Looks like reminiscent of support vector machines approaches with Gaussian. I was wondering, sometimes I know that people uses the callback Leibler divergence for proving difference in distribution. So what is your take on that? Have you tried different techniques before settling to your statistic? Yeah.
We did. We tried different kernels. I actually have a slide on this. Let me double check. We tried different kernels. We tried KL divergence. The KL divergence was not very good because it's asymmetric. And so we couldn't get consistent results. Here are some of the kernels that we did try. Let me share this. One second here. Okay, back to sharing. Okay, so here are some of the kernels that we tried, and we actually measured the performance across all our data sets, and we see that Gaussian isn't always the best, but it was the most consistent across our data. I mean, you get slight improvements, but it's mostly flat across all of them. So the intuition is not totally there. The intuition for why the network works, we have a better understanding. We have a better intuition about what's happening there in terms of this tension between the similarity in the features that are being learned by the two networks and the objective function pulling the two to be close to each other. But the thing that weighs very heavily is this reconstruction loss. And so it pushes all of the information, the sort of blip in information when the two actually come from different distributions, to manifest in the value of MMD. So we have a much better intuition about why that particular thing works. I think there's also another open question about why such a simple model works. We didn't do anything particularly. I mean, we took autoencoders out of the box and beat KLCPD, which was this variational autoencoder with all of this machinery in it, and yet a standard autoencoder network. I mean, sure, it wasn't super simple, but it's much simpler than some of the stuff we see in the literature, and it's much faster, performs just as well or better. It's very practical in that regard. I'd like to really understand where it fails, how many. There's a whole notion of like intrinsic dimension that we'd like to explore. The intrinsic dimension of the model with respect to the data. Does it have to do with the fact that maybe our data complexity is just not very high? Right, and so I think there's a lot of open questions there actually.
Yeah, actually, yeah, that brings me to the next question, right? With actually, probably you can elaborate on top of that. Is does your work suggest new theory research problems?
Yes.
And have you collaborated with your teachers, for instance, in the areas of signal processing? Yes.
The answer to the first part of that question is yes. The answer to the second part of that question is no. I believe that there are interesting theoretical questions that we're finding experimentally. And I would love to work with someone to, help us sift through that. And I have some ideas, but clearly theory is not what I specialize in. So I think that there would be some interesting results that we can and problems we can pose to prove some theories around it.
Yeah, as well as in, I think, the effort of building robustness into sensing. It's very much connected with this trade-off between theory and the need for very low power consumption at the edge that you're trying to.
Exactly. And I also think this idea of signal to noise ratio and concept learning in Maestro is fascinating. So our hypothesis is that similar events have similar structure in the data. And that's why we can detect it. But it's clear that there's noise with respect to where we're placing the device, and there's noise with respect to the physical layout of the space. And so how well we can essentially denoise an incoming signal to find that structure is, I think, one of the questions we will have a better understanding of once we do a broader deployment.
All right, we have one last question on the Q&A. Is there a possibility of introducing multimodal sensing and interrupts in the wearable sensing technologies as well?
For sure. I think the challenge there is not being annoying. Literally, like having the device, certainly the device can discover when something is new or something is out of place. But you always run into this challenge of not asking too often. There are that's certainly solvable, and it's something that the active learning community, folks who do active learning, have been thinking about for a long time. But I think the whole notion of like interaction and understanding what, that your user happens to be busy, or that, hey, humans sleep at night, you probably shouldn't ask them then, is also part of it, right? For attaining good. There's actually some prior work that's been done in the AI community about 15 years ago, where they show that if you ask at the right time with the right context, so in situ, they did it with some reinforcement learning algorithms, and the reinforcement learning algorithms actually converge faster because the quality of the feedback they're getting is much higher. And so here there's a question of, well, can we use sensing to determine when? And then re-explore those questions from before about timing and information quality with respect to timing.
Thank you. So probably just to conclude, one visionary question from my side. So sometimes I'm very much interested, in the formal verification and so on of protocols for also for autonomy and so on. And when we think about your application that you named at the very beginning, like autonomous cars and so on, but we do find, in fact, that there is still a debate in terms of which sensing architectures could be the most promising in that domain, with different school of thoughts, right? Between camera and the LiDAR and the radar and different costs and so on. So I was wondering just if you've ever thought about that domain as well, or whether you are aware of the state of the art right now, or the state of the practice or discussion.
I think the question that I've had with some of my collaborators is, which sensors provide the information we need to do the thing we want to do? So we have this oversampled, overmeasured space. There's a concept we want to learn, and essentially what we want to do is run a big ablation study of just removing different sensing modalities and measuring the performance. And no, you actually need the sensor if you want to do this class of thing. You actually need, the physiological measure if you want to do this class of thing. So I think that's definitely a question that has come up. And I think, at least in this context, we have at least an experimental framework to explore that. I think even with Maestro, determining that for ambient sensing would be interesting. Of, you know, as we build up the testbed, just the ability to turn sensors on and off and still try the same algorithms to measure their robustness with respect to the information that's available is another thing we can try.
Yeah, and this can be sometimes exacerbated by the fact that many of the things that you need might be very rare in terms of just probably happening very rare in the tails of the statistics. And yeah, but that's absolutely an interesting perspective. So, all right, so we got feedback actually. Thanks, Jorge, great talk.
Thank you very much.
On the chat, and that's also shared, I believe. And yeah, it was a pleasure to have you, and we really hope to have you in person as well as soon as possible.
Wonderful, wonderful. Thank you so much. These were great questions, and it was a pleasure being here.
And thank you, everyone, and see you all next webinar then. Thank you, Jorge.
Thank you. Bye-bye.